Section 6.1 introduces us to solving systems of equations. In this section, we will be introduced on how to solve systems of equations by graphing. A system of equations, to begin with, is where you have at least two equations that have at least two variables. So if you look at this first example, we have negative x plus y equals negative 7, and x plus 4y equals negative 8. So we have two equations that have two variables in them, in this case x and y. You can have more than two equations and more than two variables and still have a system of equations, but all the ones that we're going to look at have two equations with two variables, x and y. So again, this is just an introduction, and again, we're going to solve it by graphing. Later in this chapter, we'll learn how to solve systems of equations by using two methods called substitution, and the other one's called elimination. So again, let's just jump into it. Here's example number 1. It says graph both equations on the same graph, then find the place of intersection. So if we're supposed to graph these, the first thing we want to do is get the y by themselves so that we can find the slope, the m, which is rise over run, and the b, the y-intercept, the place where it hits the y-axis. So again, our first step is to get the y by itself. So our first equation, we have negative x plus y equals negative 7. To get y by itself, I would add x to both sides. I would end up with y equals, I'm going to put the x first, so x minus 7. The number in front of x is a 1 since there's nothing there, so our slope is 1. And remember, you always want slope as a fraction, so I'm going to write it as 1 over 1. And the y-intercept is negative 7. When we go to graph this, remember you graph the y-intercept first, then use the slope rise over run to find other points. So let's do that. So I'm going to go down to negative 7 on the y-axis, and then I will go up 1 and to the right 1. So now you can see here I went down to negative 7, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. You only really need to have 2 points in order to graph an equation, but I just did several just so that I get a nice straight line. So again, now that I've found some points on the line, I'm going to take a nice straight line. My tip to you is to use a straight edge, maybe the corner of a notebook or something when you're doing it on your own graph paper, so that you get a nice straight line, because we do want to find the place where they intersect. So if we're not drawing nice straight lines, you're not going to be able to find precisely where the two lines are intersecting. And there we have a nice straight long line of the equation negative x plus y equals negative 7. And again, I drew a long line because I want to find where the two lines intersect. So if I was drawing a really short line, maybe right here, and then my other line goes right here, but I don't extend it, I won't be able to see, if I don't draw a nice long line, where the two lines are intersecting, just because I'm not drawing a long enough line to do that. So draw nice, straight, long lines when you're graphing these. Let's move on and graph our second equation, x plus 4y equals negative 8. Keep in mind I want to get the y by itself. So my first step would be to subtract the x from both sides. So I end up with 4y equals negative x minus 8. It's easier if we put the x first. And remember, there's a negative 1 in front of that x, because when I divide by 4, I have to divide both terms on the right side by the 4. So I'd end up with y equals negative 1 divided by 4 is negative 1/4. That's our coefficient of x. And negative 8 divided by 4 is negative 2. So remember, the number in front of x is your slope, and the other number is the y-intercept. So our slope is negative 1 over 4, and our y-intercept is negative 2. Remember, only one of these numbers is negative, not both. So if I'm going down 1, I'm still going to go to the right 4, not to the left 4, because that would end up being negative 1 over negative 4, which would in turn give us a positive 1/4, because a negative divided by negative is a positive. So remember, just down 1, right 4, and we'll start at negative 2. So that's what I'm going to do. I would go to negative 2 first, then I'm going to go down 1 and to the right 4. So you can see here, when I go to negative 2 and down 1 and to the right 1, 2, 3, 4, I actually end up on our first line. So when I connect those 2 points with a nice straight long line, we see that the two lines intersect at this ordered pair. Remember, our goal was to find the place of intersection. So again, that's this point right here, because the answer to a system of equations, which again is the topic of this chapter, is the place where the two lines intersect. So again, the answer is this ordered pair right here, because that means that that ordered pair, when I substitute the number in for x and the number in for y, will give me a true statement every time, because both equations contain that point. So the ordered pair would be, I'm going to the right 1, 2, 3, 4, and down 1, 2, 3. So our ordered pair would be 4, -3, and that's our final answer. The place where the two lines intersect is our final answer for -3. And again, I can check that by taking the x value and the y value, plug it in for the x value and the y value into both equations, and it will work out in both of the equations. Let's move on and see another example. This one will go a little bit quicker just because we've already seen from the first example how to do it. So again, we're going to graph both equations on the same graph, then find the place of intersection. And this problem will actually see the limitations of solving systems of equations by graphing. So just like last time, we have to first get the y values by themselves in order to graph it. So in our first equation, -x plus 2y equals 3, I'm going to add x to both sides. So I would end up with 2y equals, and again I'm going to put x first, plus 3. Then I'll divide both sides by 2. Keep in mind that there's a 1 in front of that x, so I would have y equals 1 over 2x plus 3 over 2. So our slope is 1 over 2, and our y-intercept is 3 over 2, which really means 3 over 2 is 1 1/2, or 1.5. So we're actually going to go halfway between 1 and 2 for our y-intercept for our first equation. So let's do that first. So again, I'm going to go halfway between 1 and 2. So I'm going to put a dot right here in the middle. And then starting from that point, I'm going to go up 1 and to the right 2. But again, remember, I'm halfway up. So when I go up 1, I'm still going to be halfway between two numbers. So when I go up 1 and to the right 2, I'm still going to not be on a precise ordered pair. So you can see here, I went up 1 and to the right 2. I can do that again just so I get a nice straight line. So I have my 3 points, and I'm just going to connect those with a nice straight long line so I can see where the two lines intersect when I get the second equation graphed. So there's our first equation. Let's move on to the second equation. 2x plus 5y equals 4. So again, my goal is to get the y by itself to begin with, so I will subtract 2x from both sides. So I have 5y equals -2x plus 4. Then I'll divide both sides by 5. So I end up with y equals -2 over 5x plus 4 over 5. So you can see here we're going to have some difficulty with this one as well, since our y-intercept is not a whole number. So our slope, the number in front of x, is -2/5, so down 2 and to the right 5. And our y-intercept is 4/5. Changing that to a decimal so I know exactly where that's at, 4 divided by 5 is actually 0.8. So I'm going to have to go about 3/4, a little over 3/4 of the way between 1 and 0 on our y-axis. So let's do that first. So right there would be approximately 0.8. So again, you can start to see some limitations with graphing systems of equations by hand to solve for the answer where the two lines are intersecting, just because this is an approximation. I don't really know if that is exactly 0.8. That's just my estimation. So again, we start to see some limitations to this. So we start at that 0.8, the 4/5, and I'm going to go down 2 and to the right 5. But remember, I have to stay just below each line as I am counting down 2 and over 5, since I'm just below the line when I plotted that 0.8. So again, I'm going to go down 2 and to the right 5. So there's my second point. You can see I went down 2 and to the right 1, 2, 3, 4, 5. I tried to stay just below the line, just like I did here for the y-intercept, and I'm going to connect those 2 points with a nice straight long line. And again, our goal is to find the place where the two lines intersect. But notice here that we cannot actually tell the precise place where the two lines are intersecting because we had such difficulty with the y-intercepts not being whole numbers. And again, every time we do something by hand, there's always going to be some room for error on our part. So again, there's a ton of limitations when you go to graph equations, systems of equations, since we're doing it by hand. And every time we do something by hand, especially when we have to approximate like we did in this problem, we're going to have some problems with finding the precise place where the two lines are intersecting. So we can give an estimation as to where these two lines are intersecting, but we don't know that for sure that this is the exact point where the two lines are intersecting. My best guess on this one is we're about halfway between 0 and -1, and we're maybe at 1, but we might be just above it. So again, my approximation for the answer to this system of equations would be about -1/2, 1. But again, I'm not sure if that's entirely true because I cannot tell exactly where those two lines are intersecting. because again, I did it by hand. So that's the reason why we've developed two other methods of solving systems of equations, because graphing them by hand is not always the most reasonable or reliable way to do it, since you may end up with an approximation answer. And our last example, number 3, is where we're going to tell whether the ordered pair is a solution to both equations. Remember, the solution to a system of equations is an ordered pair where the two lines are sharing that same point. So that means the x value and the y value will work in both equations. So it may work in one, but it may not work in the other. So when you're doing these, just because it works maybe in the first equation doesn't necessarily mean it's going to work in the second equation. You have to check both. So we're going to put -2 in for x and 1 in for y into both equations to see if we get a true statement. So again, we'll put -2 in for x and 1 in for y. So in our first equation, we have 6 times -2 plus 5 times 1, and we're going to check, is that equal to -7? So 6 times -2 is -12, plus 5 equals -7. So -12 plus 5 is equal to -7. So it works in the first equation. But again, just because it worked in the first equation doesn't mean it's going to necessarily work in the second equation. So we do have to check the second equation. So we're going to put -2 in for x minus 2 times 1. So again, I got that from our second equation right here. We're going to check, is that equal to 0? So we have -2 minus -2. And -2 minus 2 is actually equal to -4, which is not equal to 0. So therefore, the answer is no. -1 is not a solution to this system of equations because it did not work in both equations. So again, just because it worked in the first equation doesn't mean it's necessarily going to work in the second equation. You have to check both. So let's move on to part B, 5(2). So we're going to put 5 in for x, 2 in for y. So our first equation, x plus 2y, so that'd be 5 plus 2 times 2. We're going to check, does that equal 7? So 5 plus 4 equals 7. 5 plus 4 is equal to 9, which is not equal to 7. So since it didn't work in the first equation, it doesn't matter whether or not it works in the second equation, because as long as it didn't work in the first equation, there's no point in checking the second equation. So once you know it's no for one of the equations, it's just no for the entire problem because it has to work in both equations. So our answers for both A and B are both no. If it had worked in both equations, then their answer would be yes. So these questions are just yes or no. But again, it has to work in both. That's it for this section. Again, this is just meant to be an introduction. We'll find other more reliable methods on how to solve systems of equations in the coming sections. But until then, if you have any questions, make sure you clarify those in class, and we'll see you then.